Okay, so in this chapter, we already discussed about the solids, the deformation in solids, just like the spring and the other objects. If the shape or the size of that object changes, so that concept is known as the concept of deformation. And secondly, if we talk about some other type of deformations, like elastic deformation, and there is a concept of plastic deformation. So in this concept, we have to know about what is the difference between elastic and plastic deformation. So basically, the elastic deformation is the same basic concept. We already know that in elasticity, when we try to change the shape of the object, so it will return back to its original position, right?
Yeah. What about plastic?
So basically, in elastic, if we connect a load with the spring or any elastic body, and when the load removed,
So when the load is unloaded, like when
yes,
you unload the weight, it goes back to the same, what's it called? Same
same
original length.
original shape or original length.
Oh, I read this in the marking schemes of some questions.
So the object will return to its original shape. And the second thing is the plastic deformation. Basically, plastic deformation, you can easily get the idea from the plastic. Let's suppose if we take the concept of that plastic sheet, if we try to stretch that plastic sheet, so you know that it will also extend, right? But it will not return to its original
Yeah.
position, right? It will stay in that.
Does this mean
Yes, the normal
is
plastic
it
is made up of polymer.
mhm.
So basically, if we slightly stretch that plastic, so it will remain in its new position. It will not return back to its original position, right?
Right.
So basically, that is beyond elastic,
Repair.
right? So basically, in elastic deformation, we only talk about the concept of elastic limit or limit of proportionality. After that, the law or the Hooke's law will not apply on elastic deformation. But in plastic deformation, when we try to stretch or try to just extend the length of that plastic, so it will change its shape and it will not return back to its original shape or original length. So basically, that concept is beyond elastic limit, right?
Yes.
So basically, plastic limit or the region or the area of plastic deformation will starts after the elastic deformation, right? Before that, the initial region was known as the elastic deformation, and after that, when we just make the curve graph, so that curve region shows you plastic deformation. So that is the difference.
Okay.
So in plastic deformation, when the load is removed, the object will return back to its original shape or length. and this will be beyond the elastic limit. So this is the concept of elastic and plastic limit, right?
Yep.
And we already know about the concept of elastic limit or elastic deformation. Further, if we talk about the graphical representation, that which region shows you the plastic limit and which region shows the concept of elastic limit. So let's suppose if we consider a graphical representation. So in graphical representation, initially both extension and load are directly proportional to each other.
Mhm.
And after that, due to that limit of proportionality, so if extension is on x-axis and load is on y-axis, so in this scenario, we can say that the initial parts or the initial region shows you elastic region.
And what does the yellow one show?
Yes, and after the limit of proportionality, because this is the point where we reach our limit of proportionality, and after that, this region is known as
Plastic region.
plastic region.
So the object does not have to be plastic in order for it to be called plastic region.
Yes, because
It just means that it's like the area after it's crossed the limit of proportionality, it will be known as plastic region.
yes, because it will not return back to its original position. So that's
Like
region.
how plastic doesn't.
Yes.
Okay.
So this is the concept of the elastic and plastic deformation and the region of elastic and plastic limit, right?
Yes.
Basically, in elastic region, load and extension are directly proportional, but in plastic limit, there is a curved line which shows you that it is no longer directly proportional to the load, right? And there are few more terms in this deformation. The other two terms are brittle and ductile material.
So like plastic is brittle, but metals are not brittle.
Okay. Because now we are having different terms, so you know that in your exam if they ask with the reference of any specific term, so we have to know about all concept behind that. If we talk about the brittle, so basically if we talk about brittle materials, so basically any idea that what is the concept of brittle material?
Brittle is its bonds are not like that strong that it will be flexible, it will just break.
Okay, so it means there will be no plastic region for brittle material, right?
Yeah, you
Like
could say.
concrete, glass, these materials
Yeah.
will break after applying load on it. So that is known as the brittle material, right?
Yep.
So we can say that material or brittle materials have no plastic region. And if we name down some materials like glass, concrete.
Or con.
So these type of materials are known as the brittle one. And if we talk about the ductile, so ductile means they have larger plastic region, right?
Okay. So like tape.
Yes. So it means those materials which can be extended after the limit of proportionality, just like a rubber material, right?
Yeah. Is this why they call it duct tape?
Yes. That's why we call that duct tape also, because you know that it can be stretched after the limit of proportionality. So ductile materials have a larger plastic region. So these are some materials, and if they ask about the graphical representation, that how to identify in the graph that which region or which type of material is ductile or which type is the brittle one,
Mm-hmm.
so you can identify from the graphical representation. So according to the graphical representation, we can say that if we talk about the brittle one, so it will be like this. And if we talk about the ductile, if you remember in the start of this chapter, we also discussed some graphical representation in which these representations are also included, right?
Yeah.
There were three graphs and we were talking about some different concept over there. So this one is the brittle and the second one is the ductile, and the quantities will be strain on X, stress on Y.
Okay. So this is the only X and Y axis which they show us? Or are
Uh,
there other graphs which we
no,
can
no. Basically, in this chapter, we are only talking about load or extension or stress or strain, right? Stress is strain
yeah.
also give you the same idea. Stress means we are applying load or applying force on the given area, and strain means the change in length, like extension. So this is the concept, right?
Yeah, okay.
And if you just check out that graphs again, these are the graphs when we were talking about the tensile strength. So in this graph, you can see you are also able to identify the ductile and the brittle material, right? Like the second graph is like the ductile material,
Yeah.
and you can also identify the plastic deformation and the ductile materials, brittle materials in that. Okay, so you can also
Okay.
identify. And after that, we already know about Hooke's law, so no confusion in that. We already discussed about. Yes, the last thing that we have to discuss is area under a force extension graph.
Okay.
So in this topic, we have to discuss the area under force extension graph, because normally we were talking about the limit of proportionality or directly proportional of force and extension. So we only discuss about these things. But let's suppose if we talk about the Hooke's law graph first, because we know that in Hooke's law we consider the directly proportional concept. So let's suppose this is the graph for the Hooke's law, which is completely directly proportional. So this will be our extension. This is our load or force, and you can easily identify there is some area under the curve. So we have to discuss about this area under a force extension graph. So basically, if we talk about the area under this force extension graph, so what do you think that
You're gonna get the Newton meters. You're gonna get what is it called?
hmm,
The force times the extension, which will give you, I think, the spring constant.
spring constant, okay. But if we talk about any other physical quantity, because spring constant is a constant value,
It gives you moment, you could say that.
moment, and if you remember one more quantity, so that is known as the work done, right?
Right. But
Because
work done is force divided by distance. All right, it is.
no, work done
It,
is F into D, right? So we can also write
yeah.
F into X, so that will also give you the same concept. Because when we applying force on it, so body is moving in the same direction. So that's why F into X gives you the concept of work done, right? Because in moment contains the concept of the moment arm, right? The distance from the pivot point to the line of action. So that's why
Yeah.
under the forced extension graph gives you the concept of work done.
Okay.
So if we want to calculate the work done, so we can easily find out with the concept of the area under the force extension graph. And in this concept, you know that we are using, if we are talking about Hooke's law, so in Hooke's law, we know there is the concept of elastic deformation in which body restores its original position. So basically, our work done will be equals to elastic potential energy, right? Because when we
Yeah.
start a spring, right, so we are doing work, and that work actually converts into the potential energy or elastic potential energy of the body. Okay,
Okay.
so we can say that work done is equals to the elastic potential energy stored in the material.
Because work done is energy, and energy can be stored energy,
So
and
it
it
means
can be
law of
elastic.
conservation of energy. So basically, we are just converting one form into another one, right?
Yeah.
And if we only consider the Hooke's law or the material that obey Hooke's law, so there will be a straight direct proportional graph. And if we are working with non-Hooke's law, like those materials which are not obeying Hooke's law, there will be a curve in the graph. So we can also shade area under that graph, and we can also find the work done with the help of area under the graph, right?
Yep.
And then we have to split that graph into the small different shapes, and then we apply the formula of the shapes to find out the area under the graph. Okay,
Okay.
So any confusion in this concept?
No. Is this it?
And the last thing is the same. We know that the concept of elastic potential energy. So we already discussed somewhere that elastic potential energy is equals to,
Equal to what?
if you remember that formula, half kx square.
Oh yeah, half kx squared. Energy equals to half kx squared. So instead you like substitute the half mv square equation.
Yes, because we already discussed that work done is equals to the energy stored elastically in the body. So if we apply the Hooke's law, so basically Hooke's law states that F equals to kx. F equals to kx means, if we talk about the elastic potential energy, so elastic potential energy means, because if you consider this graph, so this graph gives you the concept of right angle triangle, right? And if you are going to
Yeah,
find out the work done, so work done will definitely be equals to 1 over 2.
BH base times height.
Yes, F into extension, right? So we can say that the work done is equals to half Fx. So definitely your elastic potential energy will also equals to Fx,
Half,
because yes, because we are only
but is
talking
it half fx square or no?
basically initially it is half Fx, and then if you just place that value and then multiply with the x, so then you will get the final answer half Fx square, right?
Okay.
So that's how your elastic potential energy can be derived from the Hooke's law, and your final equation will be equals to,
Half fx squared.
yes.
Okay.
So these are some terms which are related to the deformation topic, the elastic and plastic and solid deformation. There are some quantities that we discuss: stress, strain, tensile, young modulus, the Hooke's law, in different like area under the curve concept. So these are the things that is included in your elastic deformation chapter, right?
Yep.